As the heading for this section says, evaluating limits when direct substitution fails. Direct substitution will not get us to an answer in these cases. We'll demonstrate how we recognize that with example 6 by trying to evaluate this using that direct substitution technique. So we'll plug in x equals 3 everywhere we can, wherever an x occurs. And then if we evaluate this, we'll end up with 0 divided by 0. And the concerning part is that we have this 0 in the denominator. We can't divide by 0. So our first step for evaluating a limit problem is going to be to try direct substitution. Plug it in, see if you get a number. If you get a number, great, that was one of the nice cases. This is one of the not so nice cases where we have to do more work to get there because we have that 0 in the final answer of our denominator. Since direct substitution didn't work, what we have to do is look at factoring this problem and then reducing. For instance, what we have in the numerator, x squared minus 7x plus 12, will factor as x minus 4 times x minus 3 all over x minus 3. Since we have a common factor in the numerator and denominator, those will cancel, meaning this rational function will reduce down to x minus 4. Once we factor and reduce, then we want to try direct substitution one more time. So now we'll plug in 3 and subtract 4 to get negative 1. If we do that and we get a number, then we found the limit. The limit exists, and in this case it's negative 1. Looking at example 7, we could try direct substitution again, but just looking at the denominator, I can tell that we're going to have 1 minus 1 equals 0, so I don't need to waste my time with that. What we need to try to do is factor and reduce. The numerator in this case will factor as x plus 4 times x plus 2, all of that over x minus 1. We have no common factors in the numerator and denominator, so even though we factored, we can't cancel anything out. We still can't evaluate this limit through direct substitution, so we would say that this limit does not exist. In addition to in example 6 finding that limit exists, and in example 7 finding that limit doesn't exist, we can classify or describe what's going on with our function at those points. If we consider a rational function, just to draw an arbitrary one here, with some of the behavior that a rational function could demonstrate. There are two different types of behaviors that can occur whenever a rational function is undefined. Either we have a hole in the graph, or we have a vertical asymptote. If we have a hole in the graph, then we can still consider those two one-sided limits as we approach from the left and from the right. We're approaching that same value, so even though there is that hole in the graph, the limit exists. So in example 6, we were able to factor, reduce, and arrive at a result. That means that our function has a hole in the graph, at x equals 3. The second case that we see in example 7, would be a case where we have a vertical asymptote. So in this case, as we approach this vertical asymptote from the right and the left, we're not approaching a numerical value. Maybe the curve is headed in the same direction on either side, opposite sides, but the function doesn't exist, the limit doesn't exist, at least not as a number. So in the cases where we try to factor and reduce but still can't get to an answer, we would say that our function has a vertical asymptote at x equals 1. We'll look at that same idea with examples 8 and 9. Here again, we would get 4 minus 4 in the denominator, so our function is undefined at 4. We have to look at factoring and reducing. In this case, this would factor as negative, or the opposite of the quantity, 3x plus 5 times x minus 4 all over x minus 4. Here we have common factors, so that denominator will cancel out, leaving us with the opposite of 3x plus 5. Now we can apply direct substitution. We can substitute in x equals 4 and evaluate this expression to get negative 17. Since we were able to factor, reduce, and arrive at a limit, arrive at a numerical value for the limit, then we know that our function has a hole in the graph at x equals 4. In example 9, 3 squared minus 9 will give us 0 in the denominator, so we'll try to factor and reduce. Factoring out an x in the numerator will leave us with x times x squared minus 4. The denominator will factor using difference of squares, and then we can factor the numerator a little bit further using difference of squares again to get x times x minus 2 times x plus 2 all over x minus 3. Sorry, my writing's getting really bad here. Let's go back a little bit. So that's going to factor as x times x minus 2 times x plus 2 all over x minus 3 times x plus 3. Once we have everything fully factored, we see that nothing cancels. We still can't evaluate this using direct substitution, so we would say that the limit does not exist, and that tells us that our function has a vertical asymptote at x equals 3.